Swayam Prabha. Digital India. Educated India.
So let's start. Very simple. The first lesson is about the flow regimes and their classification and fundamentals of multiphase flow physics. So this is a very important sentence in Latin, nani gigantium homeris incidentes, this means standing on the shoulders of the giants, in English, which is something that I like really very much. You saw before I used the book of Lightfoot, Stewart, and Bird, and so on. In statistical mechanics, there is a book of Huang that is very, very good for me. And I think that every time that I'm giving lectures, I'm saying, where did I get these notions myself? Because I was a student, let's say, 30 years ago, but 40 years ago. 40 years ago. So, okay, I was a student studying all this kind of stuff. So it's interesting. What is happening here? Okay, in my computer I can see it. This is this is only the citation of this book. This is very interesting. It's a very nice book. It's a book of about fundamentals of multiphase flows of Brennan, Professor Brennan, and I think that is really something that opened my mind when I started reading about multiphase flows. So I suggest to read this book when you want to know more notions and so on. So, about the first thing, we need to understand when we have different phases or components, the separation among the phases and the components. Okay, there are, let's say, there is a large spectrum. You will learn. I was discussing this before during the break. You will learn that with multiphase flows, nothing is safe and secure and, let's say, reliable 100%. There is always a kind of, region of gray region of knowledge that we may have. For example, the classical separation in multiphase flows is between dispersed and separated flows. But again, between these two ends, we have something in between, okay? So, we are starting with the complexity now, okay? But let's say, the definition is very clear. A dispersed flow is a flow in which one phase is completely distributed and let's say, and dispersed inside the continuous phase, okay? So, for example, imagine to have solid particles that are floating in a fluid, okay? Or you have bubbles in a pipeline, okay, or something. Or you have droplets, like in a spray, okay? You are spraying droplets, and then you have these droplets are going around and so on, and they are exchanging heat and mass with the environment, with a continuum phase, okay? And then we have a separated flow, which are, for example, when we have two phases that are separated completely. For example, when we have stratified flows, okay? So, so they are living almost an independent life. They are separated in this way. So we have a flow, for example, water on oil. So the oil is floating and the water is going in another direction. And there is something in between, which is the interface, and we are going to study this on Thursday, okay? But apart of it, we can write an equation for the water and for the oil, okay? But pay attention. This is a very simple say distinction about the two phases. It's not so easy, okay? In fact, what we can say, though, is that in the if we have an asymptotic limit for the dispersed flows when we have a very small number, a very large number of small particles. Okay, imagine to have nanoparticles, in a lot of nanoparticles in a flow. or say we can consider this as a single phase, homogeneous flow. Okay? Of course, properties will change. So if you have nanoparticles inside the system, the viscosity maybe is going not to be the viscosity of the main flow because the presence of the nanoparticles, the heat capacity, conductivity. But we can average. We can do an average, and we can consider homogeneous flows like a single flow where we have different properties. Okay? This is the asymptotic case of the dispersed flow. In this sense, for example, this means that the nanoparticles are following the flow in all the points. Okay? So in fact, there is no difference between the velocity of the continuum phase and the velocity of the dispersed phase. So, as I said, there are different, let's say, level of separation. Okay. For example, I said about the water and the oil. This is a very typical example. Okay, and for example, consider the so-called. We are going to see that annular flow. Annular flow means that, for example, we have liquid on a pipe, around the pipe, and then we have the gas that is inside, is flowing inside. And there is an interaction. There is an interaction in terms of energy and momentum. Because, for example, the gas can create waves. And from the waves, we can create, let's say, droplets that are, let's say, produced by the movement of the gas. Because they are let's say, there is a tearing of the liquid in this way. Okay. So, is this dispersed, separated, now, you see? Then it's becoming difficult. Is it separated? Yeah, it's separated because we have liquid and gas inside, but then we are producing droplets, right? So it's also dispersed. See that are different degrees, okay? So it's always a little bit difficult. But in terms of, for example, when we are thinking about a spray, we can say that a spray is a kind of dispersed multiphase flow, okay, with the droplet that is going around. So the degree of the separation it depends on at least three factors. Let's say two factors and a mix of the two others. One is the balance about the process, the fluid mechanical process of dispersion, segregation, okay? But also the initial conditions are very important, so the boundary conditions. The initial conditions in terms of generation of the multiphase flows, or the boundary condition, again, is a generation of the multiphase flow. Then we have to consider another characteristic, basic characteristic of the multiphase flow, which is the so-called intermittency. Okay, so is it possible that the regimes are going to vary? For example, imagine to have a big bubble, so we can say, oh, this is the slug flow. So we have a flow of the liquid, we have a bubble inside. Everything is nice, but then at a given point, this bubble is going to break, or we are going to have some other phenomena, okay? A strong acceleration, sloshing, for example, that is happening and also for propellant and for space applications and so on. We have a sloshing. So what is happening, that this nice bubble is going to be, say, to produce a lot of bubbles, okay? So we are going to pass from one regime to another, and maybe back to the first one. So in the multiphase flow, we can say there is one regime, and we are going to see these different regimes, but it's possible also to have an intermittency. So we can have a time for one regime and a time for another regime, and vice versa. Okay, so the things are becoming really super complex. Another point is that, let's say, to consider is the fact that in many multiphase systems, we are going to have a difference of densities. Oil, water, solid particles, and the fluid, gas and liquid, and so on. But the difference of the density, when we have an acceleration or let's say a bulk force in general, gravity, means that we have a separation due to the buoyancy. Okay? This is the reason because we are doing a lot of experiments in microgravity, for example, in space, linked to the difference of densities, because of course, when you don't have a force, an external force, the things can change. Or maybe we can even better understand what is happening, because we are switching off one of the components of the momentum equation. And then there is another point. If you can consider, let's say, a multiphase flow, imagine to have bubbles inside the continuous, bubbles inside the liquid, okay? Liquid that is flowing. The presence of the bubbles can maybe expand or they can contract. So you are creating local accelerations. Okay, so we need to consider an equation that is much more complex with respect to what we had before, because it needs to consider the interaction between one component with respect to the other. So remember, no, we did in the first hour these shear stresses. Okay, fine, was good. Complex, but okay, plus minus we understood. But now if we have another component, bubbles, particles, and so on, the particles can cause another stress. For example, imagine that you have particles, solid particles that are going to rotate inside. No? So this rotation is producing a vortex. So it's producing extra stresses. We need to try and understanding how can we deal with the extra stresses linked to the fact that we have another component. It's becoming quite complex, right? So we have a relative velocity, okay? So for example, if you consider a relative velocity WP, the ratio of WP with respect to the mean flow velocity is a function of Reynolds. Here we are writing in terms of U multiplied by the diameter of the bubble or particle, whatever, and these two parameters, X and Y. X and Y again contains the mass. R is the particle size, and MP is the mass of the particle. L is the characteristic length, for example, of the nozzle, and V is the volume of the particle or the sphere that we have. Okay, so then let's say asymptotic condition. I have time to enter in this field, but let's say that what will be interesting is to understand how local accelerations of the dispersed component can influence the relative velocity, the mean relative velocity inside the flow. And so, as you can understand, we have buoyancy and we have acceleration, no? Because of the different density. Well, we can use this information saying that, for example, when we have, let's say, the different conditions in terms of density, we are going to have segregation of the particles, the bubbles, and so on. For example, if you consider something that is rotating and we have solid particles, a solid particle has usually a density that is bigger than the density of the continuum phase. So imagine to have, you have in a system, you have solid particles in a fluidized bed and so on, something like that, and then you have a gas inside. If we are putting in motion the gas, we are creating a vortex, for example, it's very clear that because of the centrifugal force, the particles are going to touch the wall. No? It's a cyclone system. Okay? This is interesting. If let's say the density is different, for example, if the density of the particle is smaller than the density of the liquid, when we are going to create the vortex, we are creating another situation. We are obliging almost the bubbles, in this case, to construct forms, because they are going to aggregate themselves. So you are going to construct let's say, forms like you saw here, where this is interesting because this is the velocity, the velocity of particles inside, okay, in atmospheric flow. Atmosphere is a multiphase flows. flow, sorry, is a multiphase phase system. It's quite complex, very complex, okay, with a lot of different things. And we spoke about something that is rotating, that is so the solid particles going, let's say, to the wall. The bubbles are going to build structures, let's say, because the density is lower than the continuum phase. And when we have, let's say, characteristics like in what we have in atmosphere, we are dealing with the turbulence because the dimension is very big, okay? So in this case, what is happening, we have structure like that. So we are forming clustering of the dispersed phase. So, and there are a lot of studies about this kind of situation, okay, where we can see really what is happening. Another point to say is that, so we said that now, but it's better to repeat, the particles have an effect on the turbulence level. We are going to see this later on. So there is an interplay between the two phases, okay? And it's quite difficult to understand what is really happening. In fact, for example, we can have, this is the classical condition, as I told you, of particle in a cyclone. And you can see here that the particles are going to form, and you have different conditions, no? And you can also try to simulate what is happening in this cyclone. We have a gas circulation region. We have a region without particles, and so on, okay? So, for example, is the formation of, for example, with cavitation, the formation of the bubbles is, let's say, changing the characteristic of the motion of the flow. Okay, so these are already quite complex situations to study. Okay, so they are changing the turbulence level, the turbulence intensity. So as you can understand, it's quite complex. You can see other material here if you want to know a little bit more. The formation of the bubbles is interesting because of cavitation, for example, and we may have on the opposite side, we have formation of condensation. We have formation of droplets. No? Again, they are influencing the turbulence level and so on. For the gas-liquid case, we have, let's say, this situation where we can distinguish between a bubbly flow, where we have bubbles going around in a pipe. We have slug flow, and the slug flow means that we have elongated bubbles, and they are very long usually, and they are, let's say, here you have a slug with a liquid film, okay? Which is, let's say, one typical case for pulsating a pipe. For example, I know that one of you is studying pulsating a pipe. Then we have churn flow, where we have what we saw before. So it's a kind of annular flow, but we have a lot of bubbles going around. So it's a mixture. Here is the separation again between the two phases is a little bit more complex. It's difficult to say it's separated or, well, I don't know. Then we have slug and annular. So we have the slug where we have already, let's say, the gas inside in form of bubble, where the velocity of the gas inside is pretty small. But then we have annular flow. Annular flow means that the gas inside has a given velocity, and the liquid film maybe is dragged away because of the motion of the gas. So this is the classical picture of what is happening. In this case, it's a very, very small channel, because it's a channel of 1 millimeter. I put this one and not other cases with the bigger pipes, because really I wanted to stress the fact that multiphase flows are really a multi-scale problem. So we can pass from, let's say, 100 nanometers. I know a guy in Paris that is studying the flow in nanotubes. So the flow in nanotubes. A little bit difficult. Huh? So he's putting a tube, a nanotube, and he was able to have the flow and visualize the flow that is going outside. And he was also able to measure the pressure drop. So what? It's not possible to have, let's say a manometer, a gauge, no? It's not possible. But he did this because he had an idea of the velocity of the outlet because he measured the cone that is of the fluid that is going outside. From the dimension of the cone, it's possible to do some numerical simulation and to extrapolate the velocity at the entrance and the exit. So it's possible to understand the difference of pressure. So it's a nanoscale phenomenon. The nanotubes were about 20 nanometers, so okay, small, okay, and but then we can have also big pipes. So it's really completely different, meters. Okay, so and another point, when we have particles, solid particles, we can create situations like this one. This is a so-called fluidized bed. Fluidized bed means that we have, let's say, particles in suspension. They're solid particles that are moving inside. This is very important for many applications, let's say, when we want to separate the particles and so on. We have, for example, reactors for catalytic cracking, in combustion also, when we like to produce black coal. So we have this kind of situation where we are using the continuum phase in order to keep the particles separated and convey the particles in another point. In this case, the fact is that we have so many particles, let's say, is saying that we are already in direction of a homogeneous flow. So we could consider what is this system as a single phase, but with the other properties. Okay? Of course, if you want to study, for example, the turbulence in a turbulent situation, here is quite complex because, of course, the particles has an influence. So you need many times what we are doing, not we because I didn't do simulation on that, but let's say what my colleagues are doing is to put coefficients. And the coefficient, you need to arrange the viscosity. So instead of having viscosity, you have something else. Usually it's a Newtonian fluid, at least. Usually Newtonian fluid, but then you need to change let's say the value of the viscosity in order to fit with the experimental data, for example. Okay, it's not possible really to understand, to calculate how much is the viscosity for all these kind of situations. And so you have different conditions and so on. This is a paper, for example, on the gas-solid fluidization system in powder technology, and you can see that for different conditions and so on. We are working since, look at this paper, 1949, and here is Takeuchi 96, 86, 95, 2021. So it's so complex that we're still looking for solutions or looking at very good simulations. And this is happening for all the multiphase flows. So this is not, there is no, let's say, perfect solution. We are trying always to refine something that was done in the past and so on. This is the reason why it's so important as a field. So you can do a lot of different things. For example, this is another example. It's interesting. It's a very old picture, but it's you know the Moody diagram. So the friction coefficient is a function of Reynolds number. Well, you can recognize this. You can recognize when you have a laminar flow, you have 64 divided by Reynolds, no? And then it's going down, and then it's reaching a kind of asymptotic condition. And usually here in a Moody chart, what we have is the relative roughness, no? You remember, roughness divided by the diameter. So this is what we have. Well, when we have, for example, in the case of solid and liquid, this was solid and liquid, depending on the dimension of the particles, beta is representing the dimension of the particles, you have different conditions, see? So, in fact, there is a very strong influence on the friction coefficient due to the presence of the particles inside. Again, this is, let's say, is interesting, and this is not a numerical work, it's an experimental work, and only to replicate this graph numerically, wow, is something. It's not easy at all. Okay, this is a very short introduction in order to understand what we are speaking about. The introduction was really about dispersed and separated flow in order to have the same vocabulary. Now we enter in the physics. Okay. We saw that in order to build the mass conservation equation, the momentum equation, the energy equation, we use the concept of having a small volume. We said, okay, we have a small volume, the x, the y, the z, and we did the balance on this volume. Okay? Good. No problem. The point is that when you have a second component, the choice of the volume is not, let's say, so easy. Again, okay? Before it was a single phase. We take a volume, we can delta x, instead of the x, we have delta x, delta y, delta z. Okay, I like it. We know that we have air, we have water, whatever. No? Now we put inside particles. And the problem is that epsilon cannot be everything. Epsilon is we would like that the properties of the flow are, let's say, must be very small in order that the properties are not changing so much. Okay, but also the volume should contain enough particles in order that we can understand the effect of the particles. Understand? So when you are dealing before, when we took the volume, we said the x, and then inside of this volume, the temperature was this one, the pressure was this one. So this was enough small to contain enough liquid, okay, in terms of molecules, to determine the property of the fluid. But the property were constant inside the volume. When we're putting the particles inside, we have the problem that also with the particles, we need to have enough particle. So if we have a very dispersed, and we have a small volume, but then we have only one droplet, well, this is another case. It's a study of maybe the oscillation, one droplet inside the volume. But this is not the volume that we need to consider for this kind of equations. So this is the first point, okay? The fact that we have is enough small, so you have, let's say, constant properties is important in order to have the smooth derivatives for the flow, okay? And the second one is important to have enough samples of the dispersed, of the other component, okay? The point is that it's very difficult to have, let's say, since the second component, for example, with respect to the first one, let's say, as an influence, this interplay, this interaction is important because then it's changing the properties, even in a small volume. So in fact, in multiphase flows, many times we are speaking about average quantities. We are going to speak about average densities, average velocity. Okay, so it's quite difficult to have one single value that is, let's say, good in order to have both the condition of enough big or enough small volume. So even the choice of this volume with multiphase flows is becoming a little bit tricky. Okay, and one can say, well, okay, yes, but at the end you are going to write the equations. Yes. But when you're doing numerical simulations, then you are going to notice that it's not really, this is a big problem. How big should be the cell size? Then it's becoming a problem. Okay, so because you need to have the cell size that is containing something, maybe if you are doing Euler simulations, you need to have enough droplets or, let's say, bubbles in order to have an average property which is constant inside the mesh size. Okay, but this is again not obvious for other conditions. Okay, so so this reflection is important because this is, let's say, as a consequence for the numerical simulations. Only for the notation, we are going to have the continuous phase C, the dispersed phase D. Of course, liquid, gas, and vapor, and solid is very simple, and so on. Then we are going to use J for the volumetric fluxes. So, and we are going to have that these, let's say, in the I direction is given the flux is going to be the sum of the different contribution of the fluxes. And we have also the mass flux. We are going to use the letter G. So the GA of the component A in the I direction will be rho A JIA, and so on and so on. I think that is enough clear. And then we have the relative velocity, okay? So in the direction I, we are going to have the difference between one component and the other. So UA in direction I minus U of the other component B in direction I. So we are going relative velocities. One concept that is very important is the volume fraction that we are calling alpha n, okay? So imagine to have, let's say, two components only, A and B. We are saying how much is the volume of one component with respect to the other. So this means that what we wrote in terms of J, we can write something like alpha n U n I. So the total volumetric flux will be alpha A, U, A, I, and so on. So the sum of all the components of the fluid, okay? And this is also important. So is the volume, is the fraction, is the ratio between the volume of one component with respect to the other. Of the total volume, sorry. Of the total volume. And so using this concept, we can write also the mass fraction. But I'm going to use, I think everywhere, yes, everywhere I'm going to use the volume fraction, I'm quite sure, okay? So I'm going always to use alpha to know how much is the fraction of the volume of one component with respect to the total volume. I think so. Okay. I don't know what's happening because I checked this morning and I don't know why there was a different position. I think that when we translate from Mac to this one, I don't know. But okay, it's not important. Now, we need to write the equation of conservation using, let's say, the concept that we saw in the previous lecture. Okay, the mass flow of a component can be written like, the rho of the component n for the volumetric J, okay, in the direction that we are choosing, in this case the direction I, the xi. Okay, so this is the net flow. Okay, so we can write the classical conservation of the mass. I'm not repeating the demonstration, but it's just what we have done before, in the hour before, just that. However, when we write down this, we are landing with one term, that is the mass interaction term. This is already a big change. Why that? Well, we need to conserve the mass, and we have a flow. We know that the equation is the equation that we wrote before for the single phase, only that, so we have equals 0. So, or we have the mass that is going to change inside the system, right? The rho over the t was like that, right? Okay. So okay, we can write also the total derivative. In this case, why we have a mass interaction term? Well, because in a two-phase system, we may have a mass exchange due to the fact that we are going to have phenomena inside that are transferring mass from one component to the other. So the mass conservation is going to change because we have these new things. So we are going to have evaporation, for example, boiling, condensation, sublimation. Imagine to have dry ice that is going inside the gas. Of course, we have sublimation of the dry ice. Okay? So, in this case, the mass interaction terms are really very important because they are saying the rate of mass transfer into or out of a phase n that we are considering. Okay? The mass interaction terms, as you can see from the equation here, it has the dimension of the density over time, so kilogram over cubic meter per second. And this, again, very important because in two-phase flows, we may have this kind of phenomena. Or, for example, we can have chemical reactions. Also, the chemical reactions are changing the mass of one component with respect to the other. Okay? Or we have dissolution, or we have interphase diffusion. So one phase that is entering the other. For example, we might have a liquid and we may have a gas, but the gas is going to be dissolved by osmotic diffusion. It can be dissolved in the other one. Okay? Well, this means that we are changing the mass because there are these terms to be defined. At the moment, you don't know, okay? But, okay, you will see. It's okay? You understand the big difference? Okay. So, for the single phase doesn't exist. For two phases already, or three or four, it can change a lot. So, this equation is called phase continuity equation. If you want, it's phase continuity equations because we are considering the different directions. Okay? But it's very clear that if you are considering the system, and the gas is going to the liquid because of the condensation, or the liquid is going to the vapor because of the evaporation or boiling, whatever, what is happening is that the total mass should stay the same, at least. So this means that the sum of all the mass interaction terms is all the sum over all the components must be zero. Okay. So this means that if we are summing up everything, we are landing with the final equation where in fact we have the variation of the density inside the system is equal to the gradient of the mass flow rates, considering the volume fraction, and here we have a symmetry. So we have all the components, and here now we have a zero. Because we sum all over the components. Okay, so, and already you can see that we can even consider, let's say, average values. Okay, we can have also a condition where we don't have. We could check if the particles, in fact, are staying, let's say, with the same number. If we have also to follow the number of particles. I'm not doing this. Okay, momentum conservation. I don't have time to derive all the equations. Okay, this is becoming really too much. Okay, so I'm going to write the equations and then I'm going to describe what is happening. Okay, but I don't have time for the derivation. I'm sorry for that. It's very close to what we have done in the first hour. Okay, only that now we need to consider the different end phases. Okay. But in principle, is very similar. Okay. So let's consider a dispersed and a continuous phase. Okay. So, and it's very clear that we need to write this expression that is considered either one or the other. Now is either, not and. I mean, we consider one continuous phase. We say, oh, this is the continuous phase, gas. And we're writing the momentum equation. Bubbles, or no, sorry, droplets in this case. Droplets. And we are writing the momentum balance. Okay, so one and the other. Okay, now we are not putting together. Okay, separate. This is important to say. So we are doing the same thing that we did for, let's say, during the first hour. So we are doing the balance, okay? So we are using the momentum conservation principle, and we are landing with something that you can recognize. On this point, you have the rate, the variation in time of the momentum for the end component, written in terms of the fraction, the volume fraction, because it's rho A alpha. And here you have the gradient of the momentum rate. Okay? Until now, it's fine. Of course, this is this is giving a value that we know that must be equal to the force. And now the trick, this part is known somehow, it's not difficult. Now the trick is to define what we have here. So which is this force? Okay, there are many different contributions to the force. Okay, let's start with the simple, the simplest maybe, an external force. We have gravity, we have centrifugal forces, electromagnetic forces, and so on, something. Okay, so external forces. Okay, the second contribution is due to the traction on the control volume. This is what is happening when we have water and oil and we have a traction. We have a shear stress due to the presence of one component with respect to the other. This is a second contribution. Then there's let's say the third contribution is linked to the fact that we have the force that on one component to the other component. So this means stresses, let's say. Okay. So at the end, what we may have at the beginning is something like that. This term, the total derivative of the mass of the momentum flux, is equal to the force that is linked to the external forces. Then we have what? We have the pressure, and we have the shear stresses. The stresses now. Let's see. We are speaking about the stresses. The delta is again a delta, is not the delta Kronecker, but is another delta. I'm using delta D and delta D is 0 when we have a dispersed phase, and delta C is 1 for the continuous phase. Remember that I wrote this for either the dispersed phase or the continuous phase. And this is so-called individual phase momentum equations. Okay, so now if you are using if you are using the mass conservation, we got the IN, so the term linked to the mass exchange, evaporation, boiling, condensation, and so on. So without demonstration, if you consider also that equation, and you put that equation inside the IPME, you obtain an equation that is plus minus very similar to the first one. Of course, there is a change. There is a change here. There is a change here in this part, but you are going to land with this term. If you see, is the mass that is a change, is the interaction terms, multiplied by the velocity of the component n in the k direction. Okay, so you're landing with this term, okay, and the first part is the classical total derivatives. On the other side, you have this term that is a little bit puzzling, but is very important because it's giving the variation of the mass for one phase with respect to the other due to the phase change, for example, okay, multiplied by the velocity. So imagine to have a droplet that is evaporating. Okay, so you have a droplet, evaporation from the droplet. So you have a mass that is going out of the droplet, of the liquid, and in the gas. And this is transporting a momentum. As you know, maybe someone knows about the Stefan flow. maybe. It's okay. It's not important to know. But I mean, there is a transport momentum due to the fact that we have the mass that is going to move. Okay? This was not existing before. This was not existing for the single phase. Did you get my point? Okay, so when you have a phase change, we are going to have mass that is maybe in one direction or the other, can be also condensation. Okay? So this means, for example, you have condensation. So you are producing a droplet because you have a condensing vapor. So this means that the mass of vapor is going to the droplet. So there is a movement. So we need to consider the momentum that is created by the fact that we have part of the mass from the vapor that is going to the droplet. This was not considered before. It was a single phase. Is okay? Okay. Okay. If there is, let's say, if the two phases are the same, we can say that at the end we are going to, of course, to land in direction of the single phase solution. Okay. So consider now a dispersed phase momentum conservation. Okay. So we are going to have the total derivative of the momentum flux, and in this part we have the momentum that is linked to the mass exchange, and is equal to forces. Okay? One is the gravitational force. Do you remember what I said before about the forces in two-phase flows? Which was the other one that is also very important, for example? Due to the difference of density, remember? Okay? So we have a buoyancy. This is again something that we need to consider. Okay? So the buoyancy forces are really important in this case because, for example, with the bubbles, we are going that bubbles in the gravity, if we have a gravity, of course, when the difference of density is important, is moving inside the system. Okay. So we need to understand this, but then there is another one that is not written, but I can anticipate, that if you have particles that's moving inside or bubbles or droplets, there is another force that is created by the viscosity, which is the drag. The drag, no? So if you are moving something, an object, a solid object inside a inside a fluid, you have a force that is called drag also. You have a force like lift. Okay, so in the case of the dispersed equation, we need to consider, let's say, the extra forces that are present because we have different components with different densities. And of course, for example, if you have a bubble inside the system and you're considering a drag, you're considering the viscosity of the continuum phase. You have bubble inside the liquid, right? So, of course, the bubble is moving and is moving inside the liquid with a given viscosity, okay? So we are going to consider the stresses that are linked to the fact that this bubble is moving, right? For example, we could neglect, in this case, the internal circulation of vapor may be inside the bubble, because there may be something, okay? For example, when you have a droplet, the droplet is going to be deformed. So if you have a droplet inside a flow, and the droplet has enough velocity, can be completely deformed, can be even break up. And inside the droplet, you have a velocity. So in fact, you have other stresses inside the component of the liquid that are produced by the interaction with the gas. You start to understand that it's a mess. Okay? So in fact, we are always then doing something with simplification and so on. Otherwise, here I'm presenting the most general equations. Okay? On Thursday, we are going to, let's say, along specific cases. Okay? But here I need to put everything together in order to give a kind of umbrella. Okay? And then we are going to see. Pause. Okay? The 5 minutes, sorry, but otherwise we don't have time. I can recover a little bit on Thursday, but it's better to finish at least this part today. Okay, so Are you okay? So the big difference with respect to the single phase, the mass interaction terms are really very important. And I bring these mass interaction terms with me. And also the forces are changing, because there are forces due to the fact that we have another component. This is the major message. Then mathematically can be complex, but plus minus we will see that it's not so complex when you write down equations in the, let's say, in explicit form. But in a comprehensive form, this is the way to say. Is okay? Okay.